Hi everyone. I mentioned this video that it's going to be clipped together with Dogmatic, but we decided to just post it separately because at least my section is very, very long, and it constitute of over an hour-long video if we put them together. So we're just going to post them separately. I'm still going to be collabing with @Dogmatic in the actual YouTube app, and I'm going to be linking his channel in the title of the video. So definitely go check out his video to find his solution. But here's my solution. Okay, let's look at this. I don't know if I'll be sending this over or not, if I'll even solve it here, but this is a collaboration with @Dogmatic, @Dogmatic. No matter whose channel you're seeing this on, I am Algebra. And both Dogmatic and I are math YouTubers. We solve problems. I don't know if I'll be first or last. We'll see. But, yeah, so I'm tasked with solving this problem. Find the greatest common divisor, or we need to prove that this is true for all AB. That the great, I'm assuming all positive integers, I forgot if that's the case, but all positive integers, A and B. Sorry, I need to plug my stylus in. Where's the USB? Oh my gosh. I swear I've flipped it around 4 times now. Which one do I plug it into? I plug it into that one like this. There we go. Positive integers A and B. So A and B are a part of the integers that are positive. The greatest common divisor of 2 to the A minus 1 and 2 to the B minus 1 has to be equal to 2 to the greatest common divisor of A and B minus 1. We need to prove this is true for every A and B. Okay. So, let's look at some examples of 2 to an integer minus 1. So, if we have, and then just for reference, greatest common divisor gives the product of every factor that the two numbers share. So if we look at 2 to the blank minus 1, I know that that can be prime. It's possible that that's prime. Like I know I think it's more 7 primes. There's a certain class of numbers that look like that are prime. Anyways, oops. Okay. So, we know 2 to the A minus 1. So 2 to the 1 is, or let's just do 0, and then 1, 3, 7, 7, 15, 31, 63, 127, 255, and then we could go 511. Okay. So just the factors of these, if we write it out, 0, 1, 3, 7, this is 3 times 5, this is just 31, this is 9 times 7, so 3 squared times 7. 3 squared times 7. This is 127, which is not divisible by 2, 3, not 4, not 5, not 6, not, is it divisible by 7? 70 plus 57, 57 is not divisible by 7. Okay, 7, oh, it is divisible by 9, never mind. 9, 11, no, 13, no, oh yeah, I don't need to go any higher. So this is prime 127. Why don't we write up the exponents that lead us here? That noise. Okay, exponent 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. 255 is of course divisible by 5, but what is it? It's 5 times 40 plus 11, so 5 times 51. 51 is prime. 5 times... Oh no, 51 is 3 times 60 minus 9. 60 minus 9 over 3. So 20 minus 3, 17. So 3 times 10, 17. 511 is... It divisible by 3? No. 5, no. 7. Well, 490, and then 21. Oh, yeah, this is divisible by 7. 490 is 70 times 7. 21 is 3, so 7 times 73. 73 is prime. Interesting. Okay. So if we look at the ones that are prime, this one is prime, this one, this one, this one, and yeah. So 5 and 7 are prime, and 3 and 2. So possibly it could be a pattern every odd. Exponent leads to a prime, or no, because this one isn't. Am I sure this is divisible by 7? 7 times 73, 490. Yeah, plus 21. Yeah. Am I sure? Yeah, I'm sure. Okay, so that's not a pattern. Maybe if it's to the power of a prime number it gives prime? I don't know. Anyways, so we need to find if that's equal to 2 to the greatest common divisor of A and B minus 1. I don't even know how I go about doing this. Oh, I do see something. So this is basically saying the greatest common divisor of this plus 1 is a power of 2. The greatest common divisor of both of these plus 1 is a power of 2. Okay. The greatest common divisor of these plus 1 is a power of 2. So the greatest common divisor of these plus 1 can only equal some power of 2. That's the greatest common divisor of both of these. So if A and B are coprime, that means that would mean, according to this, which I have not proven, if A and B are coprime, their greatest common divisor is 1. So that means the GCD of 2 to the A minus 1 and 2 to the B minus 1 is equal to 1. Um, hmm, 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 hmm. So if A and B are coprime, then 2 to the A minus 1 and 2 to the B minus 1 are coprime. Can we prove that that's true? That's not even what we need to prove. That's a small case of what we need to prove. We need to prove this entire thing for every possible greatest common divisor of A and B. I noticed something weird too, because this breaks, 9 breaks the odd thing that we noticed before, but it also doesn't have a factor of 3, whereas all the other non-prime ones do have a factor of 3. So, that's interesting. Um, hmm. Maybe let's find the mod of these. Wow, that wouldn't really help though. Finding the mod. No, yeah. Because let's say we find the mod of a GCD, like that's such a complex expression. I wouldn't even know how to simplify that. So, disregarding, uh, hmm. And I wouldn't even know if that would allow me to prove the equality, because let's say I take 7 is equal to 5. And you take the mod of both sides, you're losing information. You're saying that 1 mod 5, or 1 mod 2, is congruent to 1 mod 2. Which, this is true, this is not true, so I don't even think we can take mods while still being able to prove it. Okay, so disregarding that, what else should we do? I'm thinking of just doing the opposite expressions. So add 1 to both sides, take log base 2 of both sides. Did that just make such a complex equation on the left with leaving GCD of A and B on the right? I don't even know. I don't even know. I feel like there'd be some kind of theorem that I have to use because I have no idea even where to start. You know? Um, hmm. Maybe. So if I'm looking at this, of course GCD of A of whatever 2 to the whatever minus 1 and 2 to the whatever minus 1 plus 1 has to be a power of 2. So that means, of course, this has to be 1 less than a power of 2. So that means this, the greatest common divisor of this and this can't be 5. The greatest common divisor of that and that can't be 5. It has to be, these come in a pair of 16. Of 16 minus 1. You know, it has to be 15 times, you know? Um, and this has to be 8 times. 17. Greatest common divisor of this and this. No two only share a factor of 17. They share a factor of, is it 3 times 17? 3 times 17 is 30 plus 21, which is 51. No, they share a factor of 5 times 17, which is 50, and 35, which is 85. Okay, I don't know what I'm talking about. Maybe they share a factor of 15 times 17? Oh, they must. 15 times 17 is 35, 50, 70, and 100, which gives us 5, 1, 5, 255. Whoa, they share a factor of 255. So this, in and of itself, is the GCD of this, and this, 2 to something minus 1, has to be equal to 2 to something minus 1. Yeah, that's what it says. Algebra. What am I doing? That's been given for a while. That's just that'd be a very interesting fact given it'd be true, but how do I prove it's true? Can't find a counterexample, because I'm not going to find one. It'd have to be trivial for me to find one. Um, Probably, I don't know. But if you notice, this doesn't act like true prime factors, because we can disregard 5 on its own, it doesn't really matter. All we have to worry about is 5 times 3, 4, 5. Although, if you take this and this, you are worrying about the 3 factor. So the 5 goes into 3, and the 5 goes into 3, and 17 goes into 5, which goes into 3. 7 only, both 7 and 3 squared, which is 9. 3 squared goes into 7. Although 3 squared could matter on its 3 could matter on its own in the 3 squared, not necessarily the 3 squared, but the 3 squared wouldn't matter unless it's multiplied by 7. Huh. 512, what's next? 1028? No, 1024. 1024 minus 1 is multiple 3. 10, we get 1024. 1024, or 1023 I should be writing. 1023. 1023 is 999 plus 24, which is 333 times, or 333 plus 7 times 3. 333 plus 7 is 341, which is not prime, which is not divisible by 3. Wait, is it 343? Yeah, 343 is not divisible by 3. What else is it? 341, 341, 341, not divisible by 5. Not, is it divisible by 7? 341. 341 divisible by 7. It's 7, 350 minus 9, yeah, no. 9, no. 11? 121 times 3 is 363. 363 plus 2, 22. Yeah, no. Oh, yes, 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 yes. Yes, 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 yes. It's 363 minus 22. So this is 3 times 11 minus 2. So 3 times 11, 31, which is a previous contender. It's a previous contender here, we see. Yeah. So we're seeing previous numbers here. We're seeing previous, which of course would make sense if they do have a GCD of whatever we're looking at. If they do have a GCD of 2 to the something minus 1. So How do we prove this? There's no like reverse GCD operator. There's LCM. That's not the same. You can't do LCM GCD and not be equal to it. LCM times GCD equals the number of them equals them multiplied together. But there's no inverse operation of GCD, which would make sense, I think. Like that's just a two information losing of a operation to have an inverse of. Hmm. No. Um, 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 Okay. I'm gonna take a break for a while and think about it and do some research, and I'll come back eventually when I come up with something. Hi guys. Okay. I'm coming back to solve this problem after a while. In the meantime, I've done some research about how to solve GCD problems. I've learned it's good to conceptualize them in this way. So if we have GCD of A and B, this means that if we say that's equal to GCD of A and B, yeah, greatest common divisor of A and B, let's say that's equal to D to the divisor. So that means that there will be some number times D times some number, which is equal to A. So something that divides A times a number, and D times another number, and 2 that equals B. So this is a good way to just put it. And this allows us to simplify it to GCD. What am I doing? GCD of 2 to the, what is it, 2 to the A. So that means A is equal 2 to the D times N1 minus 1, and 2 to the D times N2, not 2 times N2 minus 1 is equal to 2 to the D minus 1. Okay. An interesting thing we can do is, if you notice, everything has this 2 to the D in it. And then this is just brought to another power. So if we say x is equal to 2 to the D, then we can say GCD of x to the N1 minus 1, x to the N2 minus 1 is equal to x minus 1. So the greatest common divisor of x to some power and x to another power minus 1 is equal to x minus 1. Okay. Can we prove this is true? Maybe we're able to factor this. Sorry, somebody needed me. Let's continue. X to the N1 minus 1. Can we... Well, we know x to the anything minus 1 always has x is equal to 1 as a solution. So we know that's true, but can we say that's the only solution they share? Well, if we look at this, this is some collection of points on here. This is some collection of points on here. And this is solely this point right here. So can we say the only value that these share is this? So this would have to be like this, and this be like this. But they could share, like, this could be 12, and it could be like this, and they'd share these two, which we don't want. So can we prove that n would it be, yeah, n is a power. Or is this really how it works? We have x to the n minus 1, where n is an integer. Yeah, yeah. We need to say that n1 and m1 are co-prime. Because if they're co-prime, then they don't share the same roots, but can we show that? Can we show that they are co-prime? Or sorry, can we show that because they are, if they would be co-prime, then they wouldn't share any roots? Well, if we use the Moore's theorem, we have x to the, or z to the n is equal to, or if we have x to the 4 minus 1 equals 0, then x to the 4 equals 1, x is equal to the 4th roots of 1, which is a bunch of 1s. And then, so anyways, this is equal to r to the n cis of theta over n plus 2k pi over n plus 2 pi k over n. So, oh no, I'm lying. This is, I'm writing, what I need to do is, it's 1 over n is equal to r to the 1 over n cis of, because this is 1 to the 1/4, 1 over n, cis of theta over n plus 2 pi k over n. Okay, so if we say z is equal to 1, z is equal to 1, which is equal to, if its theta is equal to 0, its radius is equal to 1. So 1 to the 1 over n is equal to 1 cis of 2 pi k over n. So really our angles, and since it's the root of 1, it's always going to lie on that circle. The angles that we have, theta, will always equal 2 pi k over n. So can we show that for integer values of n, if theta 1 is equal to theta 2. No. If n1 is coprime, the GCD of the greatest common divisor of n1 and n2 is equal to 1, then, I don't know how to use proper notation, then this implies that 1 to the 1 over n1 is equal to their intersection, using my own scuffed math notation, intersection of 1 over n2 is equal to 1 solely. Can we show that? Yes, because if the theta of all the roots are equal to 2 pi k over n, 2 pi k over n1 is equal to 2 pi k over n2, we could get rid of these from both sides and these from both sides. So it's only if 1 over n1 is equal to 1 over n2, only if n1 is equal to n2, can we show this is true? Yes, I think so, because the only thing we're doing would be if theta is equal to 0, which is if k is equal to 0, and we're dividing by k, so we're assuming k does not equal 0. So k does not equal 0. So then we can only assume that they're the same if n1 is equal to n2. But we know that's a contradiction, that's not true. Because they can be the same if they are coprime, or if they're not coprime. If n1 is equal to 2 and n2 is equal to 4. Oh, and also I've been thinking, we know they're coprime because they're defined that way. They're defined by they're defined by a over d and b over d, and a over d and b over d are coprime. So we do know that the GCD of n1 and n2 do equal 1. So now, to satisfy this proof, we just need to show that if we need to show that, how do we get here again? This has these roots, this is these roots, this is these roots. The greatest common divisor of these yeah. Because if we come here, this is defined by the fact that x is equal to 1. Here x is equal to the mth root of 1, or the n2th root of 1, x is equal to the n1th root of 1. So these are what these are. No, sorry. These are these expressions. So we are showing that they're only equal at 1, which is this. So, Yeah, so if we show that given that n1 and n2 are co-prime, the only root they share is x equal 1, then we're golden. So we know that the roots that they have are z to the 1 over n is equal to r to the 1 over n, cis of theta, yeah. So z equals theta 0, r equals 1. So just 1 cis of 2 pi k over n. So we know theta is equal to 2 pi k over n. Um, so, oh, I see our issue. 2 pi k 1 over n1 is equal to 2 pi k2 over n2, where k1 is any number between any integer between 0 and is any integer between 0 and n1, which is k1, and k2 equals any integer between 0 and n2. So we can divide by 2 pi on both sides to just get k1 over n1 is equal to k2 over n2. So we need to show that n1 k2 is equal to uh, k whatever n2 k2 solely k1 solely when if and only if k1 and k1 is equal to the k2, which is equal to 1, I think. Because, can you see that? Yeah, that's fine. It doesn't work if you see that. It only matters because, because if they're only equal to 1, then their first root we know, or no, if they're only equal to 0. Because their first root, their 0th root is right here, which is the one we're worrying about. Okay, sorry, that was another interruption. But we do know if k equals k1 and both k2 do equal 0, then we know this is true. And yeah, so that is true, but we need to show, we know if that's equal to 0, then it's true. We need to know if and only if. We don't know if it's only if. So, given that n1 and n2 are coprime, where n1 over n2 is equal to k1 over k2, if we know that this neither n2 over n1 is equal to k2 over k1, we can show that this is never equal to an integer, and this is never equal to an integer. These are both like 3 over 4 or something. This can be 1 over 4, 1 over 4. Yeah. So either this or its reciprocal are integers. Okay. Well, if we're given that n1 over n2, n1 over n2, let's say that's equal to uh, j. So we know j is not in the integers, and we also know that 1 over j is not in. Yeah. Well, No. Mhm. Yeah. Yep. Yes, Daddy. I need to prove that inequality holds between two expressions where over direction, I apologize. But if we show that, I don't know why I'm using these symbols, this isn't what I should be using. If it's not a part of, and it's not a part of the integers, then so j is equal to k1 over k2. Yeah. Yeah. And we can say just an equivalent thing, j opposite is equal to k2 over k1. We can see that neither of these are integers. What does this matter? What does this matter? Because I could be saying, yeah, sure, k1 and k2 are co-prime too. That's established, but why does that matter? Because k1 can be any number up to n1, k2 can be any number up to up to n2. It doesn't matter. If n1 is equal to 17 and n2 is equal to 19, k1 can equal 4 and k2 can equal 3, and that doesn't matter. That doesn't matter. We just need to show that this equality holds. That is that sufficient for proof though? I'm not sure. n1 k2 is equal to n2 k1. We need to show that this always holds. Or no, we need to show that this can't hold for we need to show that this cannot hold when n1 and n2 are co-prime. What did we do here? Can we do this in reverse? We took the GCD and we took the GCD and turned it into actual numbers. GCD of this and this equals D. So this times n this equals A. This times this equals B. So if we take the GCD of n1 and 2 to equal 1, then we're saying 1 times, we'll call it P1 is equal to n1. 1 times P2 is equal to n2. Yeah, so this doesn't really tell us anything. This doesn't tell us anything. Huh. Given that these numbers are co-prime, can we prove that this is not true? Let's try an example. n1 is equal to 5, n2 is equal to 3. So 5k2 is equal to 3k1. So we're trying to show that for integers up to these, it can't be true. So to make this true, k 5, I think I found it, 5 or 3 has to be equal to k1 over k2. So that means that if for the ratio to hold, 5 times, we're going to use p again, for 5 is equal to k1 times any scalar p, and 3 has to be equal to k2 times any scalar p, where p are the same. So, yeah, this has to be true. So if we know that k1 and k2 are less than, and p is an integer, so, no, this has to be on the other side. 5 times p, 3 times p is equal to k1 is equal to k2, because k1 can equal 10, 6. Okay, yes. We know this cannot be true because k1 is less than 5 and k2 is less than 3. Okay, I see how we could make our actual proof. So we know that this is untrue because k1 over k2 is equal to, and k1 over k2 is equal to n1 over n2. Is that what we got? If n1 is equal to 5, yeah. So we know that this would mean that k1 is equal to n1 times some integer p, and k2 is equal to n2 times some integer p. But we know that this cannot be true because just using the first example, but they're both symmetric, they're both the same. K1 is less than n1, and p is greater than or equal to 1. So if we just take the smallest possible value, which is the best for k, where p is equal to 1, then k1 has to equal n1, which cannot be true. So we have a contradiction. Do the same for this one, and you can see the same. Okay, that was a long-winded exploration, but just to summarize what we found that the expression is equivalent to the uh, GCD of x to the n1 minus 1 and x to the n2 minus 1, which has to be equal to x minus 1. And n1 GCD of n1 and n2 are equal to 1. So from this, we get that the only shared solution between these two must be x minus 1. Can we prove by contradiction that they share more solutions than that? So if we use the Moore's theorem, or solve one of these, we get x is equal to 1 to the 1 over n1. So using the Moore's theorem, 1 to the 1 over n1 is equal to r to the 1 over n1 cis of, or just, this is the Moore's theorem, z is cis of theta over n1 plus 2 pi k over n1. Plugging in 1, we get 1 to the, or I'm just going to use n because it's for both n1 and n2, is equal to cis of of theta is equal to 0, 2 pi k over n. So then we get the angle of both of these, which is the only thing that matters. Theta of the theta 1 is equal to 2 pi k over n1. theta of the second one is equal to 2 pi k of the second one. So for this equality to be true, when k does not equal 0, we have to have 2 pi k over n1 to be equal to, we're calling this k1, 2 pi k1, k2, k2 over n2. And then if we just eliminate both these, this we find is only true when k1 over k2 is equal to n1 over n2, which is only true when k1 is equal to some integer p times n1, k2 is equal to some integer p times n2, where p is greater than 1, greater than or equal to 1, and k, of course, has to be, k is always less than or equal to n, not less than n. So going with the easiest case, k1 is equal to n1, which is a contradiction because k has to be less than n. So this is not true. So that means that therefore the only possible solution is when x is when n1 or when k1 is, oh, sorry, shouldn't I go to bed alarm? Is when our only possible solution is when oh, yes. Our only possible solution for these is when x minus 1 is the greatest common denominator of this. Whereas if x minus 1 were not the greatest common denominator of this, then we would have a contradiction. And then substituting these back, we get this, as we see. I don't know if this is even a valid proof or what dogmatic did, but as you remember from the beginning of this long-winded proof, this is a collab between the two of us. And yeah, thank you for watching. I'll see you guys. If you'll see his video next, you'll see his video next. If I'm at the end, I thank you for watching. I'll see you guys tomorrow, and goodbye. If not, yeah, have fun. Bye.